you decide you'd like to go elsewhere because you thought this was going to be a Google Cloud talk, but please do so now if you would. So, I have to say, it's been among my greatest honors to have spent the last couple of days with you. I've never been to India before, and after only 2 days, actually after only about 1 day, I felt right at home. Everyone with whom I've spoken at this conference and all of the audiences have been just lovely and wonderful, and I have to say that Dilip and his team, and Naveed, who's running around like a madman and taking care of us, it's been wonderful, and I thank you all very much for having me. So iOS computer vision and computer vision-based augmented reality. So earlier today, I spoke to you about what I call geographical augmented reality. So you know where you are, you know which direction you're pointed, and you put a marker on something because you can calculate where it is. This is a somewhat different thing. This kind of augmented reality is the kind where you're taking pixels off of the camera, generally trying to do so live, and taking those pixels and doing something with them, namely trying to figure out what's in the view of that camera. There's several ways that we can do this. So I'm not going to read this to you. That's sort of the abstract of the talk. The really wonderful thing about what we do as mobile developers and where we are in history is that all the stuff that we've read in our Heinlein and in our Stephen Baxter and all the science fiction books that I know many programmers enjoy, it's actually starting to come true. We now have sufficient processing power in our pockets, we have sufficient sensors, and it's only getting better, so that we can actually use some of these canonical computer vision algorithms that have only been available in desktop computers and before that in so-called supercomputers. And there are some computer vision libraries out there, namely one called OpenCV that's fairly common, that have put together just decades and decades and decades of really, really hard research, things that is way above my head in most cases. And so we can build these things into our apps. In fact, in iOS 5, they're using a thing called the high wavelet feature detection to find faces. And now we have an SDK that's just available to everyone who writes for iOS that allows us to find faces. I wrote some code that grabs faces from OpenCV a few months ago, and I can tell you that whatever they're doing is insane and very fast, because I wasn't able to recognize a face in anything less than about a second, and Apple's able to recognize faces in real time. So this is only going to get better. So we're going to talk about the fundamentals of computer vision. We're going to talk about a little bit about OpenCV, which is the sort of canonical way of doing computer vision these days, how to access iOS device camera input, how we can tie all this stuff together to make amazing vision-based applications. So there are some slides on here that have quite a bit of text on them, and it's rather a bit too small. I apologize. I wasn't expecting this resolution. So if you're in the back rows and you start noticing that text is difficult to read, please feel free to come forward. So first we're going to talk about camera input from AV Foundation. We talked a little bit about this this morning. We're going to go a little bit deeper into it. This morning I told you how to grab that camera input and just throw it up on the screen. Today, this afternoon, we're going to take that information, pull the pixels out of the buffer, and figure out what's in those pixels. Then we're going to talk very briefly about a very small open source project that I put together that makes it easy to build and use OpenCV on iOS. It used to be a very painful thing, now it's quite simple. And some neat things you can do, recognizing images, recognizing so-called augmented reality markers, and some other cool stuff that's in there if there's time. So, AV Foundation. Again, we talked about this a little bit this morning. I'm going to go over some of that again. So AV Foundation is the API through which we can get audio and video capture and display, and so we can spit out sound as well. We can get access to video metadata and get access to timing. It's very low level, and so we can get different kinds of data off of the camera very easily. And then again, you can get the raw pixels, and once you have the raw pixels, you can do a lot of interesting things with them. So here's a block diagram of AV Foundation. This is from a WWDC video from 2010 called Using the Camera with AV Foundation. This API has not changed very much since then, so I suggest if you want to dig deeper into how AV Foundation works, check out that video. I think there's a 2011 session that's similar. Perhaps look there first. So AV capture session, as mentioned this morning, is the sort of routing framework. It's where the inputs come in and where the outputs come out. So an AV capture input may be a camera, maybe the back camera, maybe the front camera, or it could be a microphone. It could be the microphone in your little clicky thing that you have in your earphones. Or it could be the microphone. Did I say camera just now? Microphone in the clicky thing. It could be the microphone in the phone. So that all goes into an AV capture session, and then an AV capture session has several kinds of output. You probably can't see here, so I'll read it. Right here we have an AV capture video preview layer. That's what we spoke about this morning. It's a core animation layer that allows us to spit out directly what's coming in on the video camera, just straight to a core animation layer, which you can move around and do whatever you want to, just like you can with any other core animation layer. Excuse me. And then AV capture session will route data to AV capture outputs. And those AV capture outputs can be pixel buffer, they can be the screen, and they can be something to capture the audio, if you like. So to display video, I'll show you this in a second. You can set up a view-based project. You have the AV Foundation core video and core media frameworks. And then you set up a capture session, which again is that routing object. And then you set up a preview layer to show the video. Actually, I think I have the code. Default view controller, AV Foundation test view controller. You can just add two properties, an AV capture session and an AV video preview layer. AV capture video preview layer. Goodness, Objective-C and their long names. So again, the AV capture session is where you capture the pixels off the camera, and the AV capture video preview layer is where you send those images. All right, here's the part where you might not be able to see if you're in the back. If you can't, come on forward. I'll pause for a second if you'd like. You see okay back there? Good? Okay. I tried to make them bigger than I had them this morning. So the way we do this is we use an object called AV capture device. There's a class method called devices with media type. And so you grab the media type video. There's also media type audio. And then to get the device that is a camera, you iterate through the devices and you ask for the camera that you want. So in this case, we asked for AV capture device position back. So that's the back camera, the one where the Apple logo is. It's pointing toward you if I'm holding my phone up. You can get AV capture device position front if you want to, say, show the user's face. And then AV capture device input, again, that's the way that we route inputs into the routing class. So we go AV capture device input with camera, and you would normally put some kind of error handling in there. And then again, there's an AV capture device output, and that's where we're routing the information out. And so there's this thing called CV pixel buffer pixel format type key, and what that allows us to do is say, I want 32-bit blue, green, red, alpha. Who's familiar with pixel formats? Okay, so the short version of the story is with 32-bit BGRA is that you have a buffer full of pixels that's coming live off the camera, and they're 32 bits in depth, and you get blue, green, red, alpha, blue, green, red, alpha, blue, green, red, alpha, blue, green, red, alpha, until you get to the end. And so you shove that into this little video settings dictionary, and then you tell the capture output that this is the video settings that you want. Once you have that, you create the routing object, the AV capture session. That takes the inputs and shoves them through to the outputs. Here is where we say how big we want the image coming off the camera. If it supports 640 by 480, and if I recall most of them do, we set the session preset to 640 by 480. This is, if you look in the header file, we'll do that in a second, you can see that there are other session preset sizes. And one of the things that you'll find when doing computer vision kind of stuff is if you can minimize the number of pixels that you're processing, you're going to be better off. And so sometimes I'll set these to lower values, run whatever algorithm I plan to run over them, and see if I can get good recognition off of fewer pixels. And then the capture session, again, is the routing object that's adding the input and the output. And then, at least in this case, and we're going to do something different than this in a few moments, we take the AV capture video preview layer and we create a layer with the session. So we've got this capture session and it's all set up, and we say, okay, I just want a preview layer, I want to just stick this video on my screen, and then stick it on the screen. Does anybody need to see the earlier slide for information on there? I know I went through it kind of quick, just briefly. So here's how we set it up. Get a capture input, get a capture output, set the settings, and then get a capture session, take the input and the output, and then right now what we're doing is we're throwing that output on a preview layer. That's not what I want. That's what I want. So some of the other preset types. One little trick in iOS development that many of you may know, if you hold down Command and then you click on something, it will take you to its declaration. But we're not really able to do much with it right now because that video preview layer just sort of shows us whatever's coming in off of the camera, which is great for when we're doing our geography-based augmented reality because, we can hold the thing up and it just shows us whatever it sees. And what we're doing is getting information from the compass and the accelerometer and the gyroscope to figure out which direction we're pointed, and that's wonderful. But in the case of this particular kind of augmented reality, the computer vision sort, we really need to get those pixels. And so that's why we set up the pixel size a little bit earlier. So we need to make a delegate to handle frame data. And then inside of that delegate, we set up the handler. So AV capture session has a really, really long AV capture video data output sample buffer delegate. So that 3 times fast, or 3 times at all. So in order to create that, we have to set up a frame processing queue. Who knows GCD? Okay, so GCD is a Grand Central Dispatch. You don't really need to know very much about it to do this, but it allows you to do work inside of things called queues. And those queues, there's a main one that just sort of lives on the main thread where you can put little work objects. And in the case of this, what we're doing is we're setting the sample buffer, and we're just sticking it on the main queue. We can set it on a background queue. There's a few things that you need to do to be able to do that without causing difficulties. But yeah, okay, so the AV capture video data output sample buffer delegate needs one of those. Capture output, AV capture data output, data output sample buffer from connection. So the AV capture connection that you made that represents the camera is going to spit out however often it can, and you can tell it how often you want them. You can also tell it whether you want it to drop unused frames or not. So when you get the sample buffer, the CM sample buffer reference, you get a CV pixel buffer reference from that, by going cm sample buffer get image buffer. So what that will do is we'll create a CV pixel buffer reference, and inside of the CV pixel buffer is just the array of pixels. Then we lock the base address, and a lot of this AV video stuff is happening in a background process. Actually, it's happening in a separate process from your application. There is a vending daemon that runs in the background. And so one thing that you'll notice when you're doing this kind of stuff, that suddenly the CPU on your device is at 30 or 40% when you're not really doing much of anything, and that is because this background process is actually processing pixels for you, or pulling pixels in and putting them in memory for you, and that actually takes a little bit of effort. And so you might find that your app is slow, and then you run it in instruments and see that there's really nothing much going on. And in some cases, that's because this background process is doing stuff. So I encourage you, when you're doing this, to run the instruments that allow you to see sort of more globally what's going on in the phone, or the device, I should say. So we lock it, and that's essentially because there's a lot of background processing going on when we're doing all this camera stuff. And so we lock the base address so that we know that the camera isn't going to rewrite into that base address. Now that we've locked that base address, we get the CV pixel buffer base address of plane. So image data that's coming off of the camera can be pulled in what's called planar data. Who knows planar video data? Planar data? I have a slide a little bit later that explains it, but to suffice it to say, in the case of BGRA, we've got one plane. And so all we do is we say, give me the pixel buffer with the plane at index 0 from this image buffer. Then we can get the width and height of that, and then we can figure out how many bytes we have in each row. And then if we want to do something cool to the pixels, we can just iterate them. And then when we're done, we always unlock the base address. So what we're doing is we're getting an image buffer of the pixels. We're figuring out where its base address is. We're finding out the width and height. And then once we know the width and height, we can iterate through that array of pixels. This is a common mistake when you first start working in AV capture sessions, so that's why I'm mentioning it. Modifying those pixels inside of that buffer is already after it's been blitted to the screen in that layer. So in order to get those onto the screen, the simplest, well, not necessarily the best, but the simplest way to do that is to just remove the preview layer, add another layer to this view, like a plain old CA layer. We set the transform because essentially the camera's transform relative to the screen is rotated 90 degrees. So the upper left of the video camera, when I'm holding the device like this, is actually over here. All right, so we just have to rotate that. And then we draw it into a bitmap, and then we can set the contents of the layer, I should have said, not the view, to that bitmap. And I'll show you how to do that. Come on. Slide over. There we go. So there we go. We create a CA layer called the processed video layer. And because earlier on we could have set the sample buffer to be on a background queue, I always make sure that I call perform selector on main thread. The CA layer, like the plain old CA layer, you can set as contents. You can set those contents to a CG image. And we can get a CG image out of this really easily by simply creating the image, creating a new context, drawing those pixels into that context, sticking it into and then sticking it into the co-animation layer. And we build and run that. Something I forgot to mention in this talk, I tried to upload a lot of sample code this morning. through the internet connection here, which is a bit of a mistake. So I'm going to put my email address up at the end. If I forget, please remind me. If anyone wants any of the code that they see here, please feel free to email me, or if you have any other questions. And apologies, I should have done that at the hotel this morning. But I'm still a bit jet lagged. So now we're building run that. How do I switch to this thing? I think it's... Oh, it's showing me this side. Cool, I can show you my face. Hello. So you can see that I'm modifying the pixels in real time. You can also see that it's a little slow, right? You guys see that? A little bit difficult to see because it's focused down here and it's hard to hold all the way down there. But anyway, you see that I looped through them, and I looped through them on the CPU. If we have time, I'll show you a little bit later how to go through them on the GPU. But suffice it to say, we now have the ability to grab pixels. Can we switch back to slides? To grab pixels from the camera and then do something to those pixels and then stick them up on the screen, even if it is just a tiny bit less than optimal. So okay, the part that we saw earlier, where we're just going through and iterating through each pixel, and we're messing around with blue, then green, then red, down here. And once we have that, we just create a CG color space ref and a CG context ref, and stick that information into a CG context, bitmap context. And then you get something like that. So it's kind of slow. There's a lot of copying of data, and we're enumerating the pixels on the CPU. We could do quite a bit better with the fragment shader in OpenGL, and if we have time, I'll show you that. If not, again, I'll email you an OpenGL sample, and my email address is at the bottom. So if you want to write that down or type that in, I'll send you the sample code. So jsaggau@soundsbroken.com if it's too small. Hope not. So getting the gray channel. There's a reason that we might want to get just black and white image data. When you're doing this sort of image recognition algorithms that we're about to talk about, very often they work best on simple grayscale image, in part because we don't have to deal with going through and get blue, green, red, alpha, blue, green, red, alpha. We can just say grayscale, 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 so we can do a quarter as many pixels. So the way we get that is to ask the camera for planar data. Planar data is the way your old school TV used to work. So the reason that the black and white TVs would still work when they were getting a color television signal is because they were ignoring these so-called interleaved samples. And so they look like kind of like this. So this is what you get out of your TV, right? And this is what you would normally see in black and white. And then you add these two things to this thing, and you get this. All right, so they're three separate channels. Oh man, that's way too long. Anyway, that's where that comes from, a Wikipedia image. So the way that we do that is, this all looks very similar to the way that we set up the AV capture video data inputs and outputs and such. But here we're asking for, forget about all that stuff, biplanar full range. So again, planar data allows us to grab just the gray plane. And the cool thing about this is that background process that is running all of that video capture stuff, when you ask it for BGRA, is actually converting that which is native off the camera, this planar stuff, to BGRA for you. And so you'll see the CPU usage of that background process drop quite a bit when you end up using this, and that's because it doesn't have to go and convert it before it hands it off to you. So to get the luminance plane, and the luminance plane is just the grayscale stuff, we do something very similar to what we got before. We grab the image buffer, we lock the base address because there's some stuff going on in the background process, and then all we do is we say plane 0, and plane 0 of the image buffer is going to be this grayscale planar data.
All right, so now we're getting to the meat and potatoes of augmented reality. So what we need to do is find something in a scene, and it helps to make that something kind of unique and contrasty. Our friends Qualcomm, who are here today, have an augmented reality SDK that does some AR marker kinds of stuff. And so this is a fairly common means by which to do that. They're usually square. They usually have a nice black border around them. So what you can do is you can use an edge detection algorithm. And in OpenCV, there are some edge detection algorithms that will allow you to find that square. And then once you've found that square, you can dig around inside and find the edges inside and figure out what that bitmap might end up meaning. So you can encode a number in there, for instance. So how do we recognize a specific AR marker in a sort of real-world scene? There's a library called ARUCO, I think is pronounced, that will find it. And that library uses OpenCV. So again, OpenCV is open source computer vision. It's a library of programming functions for real-time computer vision. So it's not generally meant for go crunch data and spit it back, but it does do some of that too. They're fairly optimized. They're highly optimized for ARM. So I'm kind of hoping at some point we get an ARM iPhone. Not ARM, x86. They're highly optimized for x86, so I'm hoping we get an x86 iPhone at some point. And it used to be enormously difficult to build OpenCV on iOS, but not anymore because I made a little project. If you go to github.com/johnmarimba/opencv-ios, you can download it, and what it does is every night there's a cron job that runs on one of my servers that updates a GitHub project that has the OpenCV source in it, and every now and again I will go in and build the Xcode project that will make a static library of OpenCV for you, and that part's manual. And so I think April was the last time I snapshot OpenCV. And so you can get an OpenCV snapshot from 6 or 7 months ago, and I'll snapshot it again fairly soon. I try to do it every three to 5 months. It's been a little busy. But then once you download that own project as having this project as a dependency, and it will you can set it to compile all of those libraries. It also has zlib and libjpeg and libpng, some of which actually come on the phone, but I've had some trouble with having OpenCV use the ones that come on the phone. And what it allows you to do is use most of the major sort of chunks of OpenCV will cross-compile for ARM for you, and it will compile it for x86 when you're on the simulator. So Ayuko, see if I still have an internet connection. Yay. So it's a little library for augmented reality applications based on OpenCV, and actually runs pretty well on iOS. So it requires OpenCV that's greater than 2.1. I think we've got 2.2 in my project, and it will actually simultaneously grab, I think, up to 24 of it says markers. I usually do one marker at a time. But what this algorithm let you do is allow you to do a 3D transform to the marker. Or you could just use the new Qualcomm SDK, and I know they're here. It's really good. I haven't done a lot of playing with it, but what little playing with it I've done is way faster than anything I've been able to find or build myself. And hats off if they're in here. Well done. So in OpenCV, there's this thing called an IPL image. I'm going to say IPL image because I don't like saying letters over and over again. You need to be able to create an IPL image out of the incoming video stream to be able to pass it to OpenCV. So any other OpenCV algorithms are generally going to use this IPL image to represent image data. And so this is a sort of generically useful means by which to get that information out so that you can then pass it on to other computer vision algorithms that you might find in OpenCV. So we get the usual image buffer stuff. And the easy thing that we do is we make this a .mm file, and making a file .mm will tell the compiler that you're using Objective-C++, and OpenCV will then not freak out when you try to create an IPL image. And you just say CV create image, which is how you make an IPL image, out of the width and height. You tell it that its bit depth, in this case, is 8 unsigned. And then the width is 4, and that's for the BGRA input that we had before. And then you set the image data pointer to the base address, and you just cast it to a car star, and it just works, because that base address is the start, and the OpenCV library will just take that buffer and look at it. Make sure that if you're going to do anything with the IPL image outside of here, where that base address may no longer be valid, that you keep the lock on it, and otherwise that image data may go away. So the way we recognize markers using this AR-UCO library is we just pull out the source from the AR-UCO library into the project that I was talking about before, and then inside of a try block, because this OpenCV thing will sometimes puke, and we have a lot of C++ code that uses try. Not a lot of try happens in Objective-C land, so I just wanted to mention that normally you don't do those, but in Objective-C++ you can feel free. So you get the width and height. You resize the OpenCV image. So we're shrinking it down, and the reason that we're shrinking it down is that the how do I explain this? Well, suffice it that there's a whole lot of data here, and one of the things that OpenCV is really good at doing is resizing images, and so we chop it down, and then we create a vector of markers, and the marker object in our UCO a marker object in our UCO has the location. It finds the location of a marker inside of the IPL image. So a CV mat is something that you can sort of magically convert OpenCV images back and forth. CV mat is an array object in OpenCV. That's mat stands for material. And then we just tell the marker detector to detect this mat image and dump it into this vector called markers, and then it finds them. And hopefully I have a screenshot of that, because no, I don't. Where'd it go? There we go. So you see that little green rectangle? So maybe you don't. So what our UCO is doing is, inside of OpenCV, it's finding the edges of this big old box. And then inside, it's finding the edges of all the little boxes inside, and then it's figuring out, just by iterating across them, like what number this might be. There are several bitmap markers that you can make for this. So, other interesting stuff. Conveniently, all of the iOS devices that are able to do this kind of thing, are fast enough to do this kind of thing, also have OpenGL ES 2.0, which means we can get a programmable pipeline and we can process the incoming video. So a friend of mine is a fellow called Brad Larson. He lives in Wisconsin. He's one of those super genius types that I've been talking about all week. So you can add him to the pantheon of my favorite iOS developers. And he wrote some code that's really interesting that allows you to place a virtual object over a real-world object by simply tracking its color. There's no way you're going to see that. Okay, so here's what it's doing. As each one of these images comes in, it takes that and it dumps it into an OpenGL texture. That OpenGL texture is then sent over to the video card, where it's processed by a fragment shader. Who knows OpenGL ES 2? Okay, so the fragment shader is one of two shaders that you have to load when you're doing OpenGL ES 2. There's a fragment shader, and there's a vertex shader. Vertex shader allows you to programmatically modify the mesh of the objects that you're using in OpenGL. And a fragment shader allows you to modify programmatically the pixels themselves. So there's a function up here at the top called normalize color that just does the dot product and divides. And then mask pixel is when we tap on the screen, we'll grab the pixel value of whatever is underneath our finger. And then once we've figured out that, we want to figure out how far away each pixel is underneath from that chosen color. So let's say we've got something that's very red. So I tap on the screen and I get something that's very red, and then I figure out which images are fairly close to that red color. And then when I have a sort of a good approximation of which pixels on the screen are pretty close to that red color, I can then create a mask that sits in the center of gravity of that red color. And I'll show you how that it looks like that. We're finding and tracking interesting stuff in the real world. There's a thing called fast corner detection. How much time do I have left? Where's that fellow? How much time do I have left? You just screen it. It's okay. About 5 minutes? Okay. Thank you. Well, I'll just tell you what FAST is, and then you can download that code. So FAST is a feature detection algorithm that allows you to find the corners of things fast. If you go to the URL at the top there, you can find an implementation in C that's actually fast enough on iOS devices. And so one of the things that you could do is if you have an image recognition algorithm that's slow, say it takes 3 or 4 seconds to find an image, you can then use these edge or corner detection algorithms to figure out which direction the overall image on the screen is moving and track it that way. So there's this is BSD licensed. It works on iOS devices and it lives up to its name. And you can find a reference port for iOS from success-ware.com. It's $200 for commercial use to use the wrapper code commercially, but it's a really nice little wrapper for fast. So if you want to download that and run it on your phone, you can see all the edges. That's actually me sitting in my office. So I often use this to track an object which I found by other somewhat slower means. Now surf is called speeded up robust features. What that's doing is it's doing feature detection. So this is a little bit different from edge detection. What it's doing is it's taking little circles and it's placing those circles over the top of an image. And as it grabs those circles, it sort of averages out the colors and figures out the shape of the image, and it makes a sort of database of the features that are within that image. There's an implementation available in OpenCV, and if you download my OpenCV build it for you code, there's a surf demo in there that actually on the iPad 2 takes about 4 seconds to find an image that's about 200 by 300 pixels in an image that's about the size of the screen. And so what you can do then is if you're looking for, say, that Altoids tin, and you can see that this Altoids tin looks very similar to that one, but it knows that it's that one because of the features inside of the Altoids tin. So it's a really nice way to find something very specific inside of an image. So it uses hard orbit detection, and hard orbit detection, it takes a series of little boxes, and it throws those little boxes over the top of the thing to figure out what it is that you're looking for, and then it takes that series of little boxes and throws it over the top of the next thing, and once it finds a similar series of little boxes, it goes, oh, that's a similar thing. This is how face detection works on iOS 5. It uses the high wavelet transform. So SIFT is similar to surf. It's actually a little bit slower on the iPhone, so I'm going to kind of hop over it. But the good thing is that 2 or 3 years from now, it'll probably be quick. And I think that's it. I'd like to show you SIFT, I should say surf very briefly. Got it? So it's going to show you the grayscale version of what I was looking for first. And it's doing it on my simulator. Hang on. So the first thing it's doing is it's running this edge detection, this high wavelet detection algorithm over this image, which should show up on the screen, I hope, pretty soon. That's a conference that I did in Boston earlier this year. And then it's looking for that image inside of this larger image. You can see about how long that took. This is fully optimized, no thumb, ARMv7 code by running the new LLVM3 compiler. It's actually quite a bit faster than GCC was. And so you can see that once you have that, you can do a 3D transform to find it, and then, thank you. And then once you do, you can put stuff on top of it. And I've got some code that puts stuff on top of things. Again, email me if you need it, because I have run out of time. There's some other interesting URLs I'd like to throw up here at the end, if we could switch back to the other thing. So there's parallel tracking and mapping. This is actually an optical flow algorithm that allows you to take an image and then as it moves around to sort of figure out which direction all these pixels are going. I really want to implement this on the iPhone. I haven't had time to work on that yet. There's a GPU-based implementation of the CLT feature tracker. This feature tracker is actually a really good one. The GPU-based implementation is currently for regular desktop video cards, but it has some vertex and fragment shaders that I think we could port over. And then OpenCV AI is this more than technical article you should check out, which I think I can still get on my screen. Say again, please? Oh, yeah, I don't know what they're using to do that. If I were to re-implement it, I would probably do something on the GPU.